just to recap where we got to last half term, we were talking about binomial probability distributions, and this was when you had a situation which had a particular set of properties where it meant that the probabilities were predictable. And so those particular set of probabilities were when you were doing something a fixed number of times, and where every time you did that thing, there was a success-fail criteria. So, you know, some games and sports do just have win-lose, but if it was something like a game of football, then you'd have to slightly sort of modify things. So, you know, you'd say, right, that team is either going to win or not win, which includes drawing and losing. Probabilities had to stay the same throughout this whole sequence of whatever it was, and one event had to be independent of another. So, you know, if I won the first game, it had no effect on the chance of me winning the next game. And so, we used a number of examples. I want to return to chess. I've been struggling with my chess over half term. Still no better. Well, I've just crept above 700 for those that it's all a bit depressing. So what I want you to imagine is that I take on, and I'll use one of my year 10 students. They're all, some of them are into chess. I take one of them on for 20 games over a period of a half term, and they're ranked higher than me. So let's say the chance of me winning is 0.25. So the number of games that I win in that series, I'm going to call that X. X is the number of games that I'm going to win. And we say that the number of games I win can be modelled as a binomial distribution where n, the number of games, is 20, and every time I play a game, the chance of me winning is 0.25. And so what we can do is we can work out the probability that I lose every game. That is 0.75 times 0.75 times 0.75, 0.75 to the power of 20. Or we can work out the probability that I win one game, which would be 0.25 times 0.75 to the power of 19. Except that's the probability that I win the first game, and I could win the second and third, so we do 20 times that. And we can carry on. The good news is we don't need to work out those probabilities because our calculator does it for us. Arthur, what would we expect to happen? How many games would you expect me to win?
5.
Yeah. 20 times 0.25. Probability of me winning is a quarter, you'd expect me to win a quarter. So what we could do is we could work out all these probabilities from I win none of them to 20 of them. 21 possibilities, which is where our little, remember that conundrum we had shown about half? That's 21 possibilities, not 20 possibilities, isn't it? And we're saying we expect 5. So the probabilities would look a bit like that. Now that's misleading because this is discrete data, so actually you've got the probability of 0 and the probability of 1 and the probability of 2, and they'd be bars, but we tend to use these graphs just to sort of summarise those probabilities. So let's say we do this and we get some surprising results. Let's say that we do it and I only win 2 games. And then we do it again, another 20 games, and I only win 1 game. Now, you know, unlikely things happen. It is very unlikely that you're going to win the lottery, but every week, well, almost every week, someone does. Unlikely things do happen. So it could be that me only winning 2 of those games, or me only winning 1 of those games, is just something really unlikely. And unlikely things certainly do happen. But there is another possibility. Could anyone describe what the other possibility is if I only win 2 or 1 of our 20 games? What do you reckon?
The probability of you winning was wrong.
Yeah, I might have been wrong. That might not be correct. And the unfortunate thing is that we've got no way of absolutely definitively saying whether it's just an unlikely thing has happened or I'm wrong. So all we can say is, right, this is the threshold below which I'm going to say that's so unlikely that we might be wrong. And below that threshold, I'm going to assume something's wrong here. So what we're going to do today is we're going to look at how we can test in a situation whether an unusual event is just an unlikely thing, or whether it means we've got something wrong. Or sometimes, not we've got something wrong, but we're maybe overstating the case. Maybe I'm being a little bit too optimistic about my chess ability. Maybe it's nowhere near that. Or rather, maybe I'm a company that's exaggerating the claims for the efficacy of its medicine or the capacity of its, the number of sweets in its sweet packages. Maybe we're being misled here. This branch of maths is referred to as hypothesis testing because we are testing the hypothesis that this probability is incorrect. So that is going to be my objective as soon as I've located a ball drummer. We're going to talk today about hypothesis testing, and I'm going to use my example here. Who is Ollie sat next to? Ollie, are you and Harrison on speaking terms? Yeah. Good. So Harrison, are you able in a minute to get Ollie up to speed as to how we can use his calculator to work out these probabilities? Yeah. That would be super. What I would like you to do for me is in that scenario, and this is everyone, in that scenario I would like you to work out some probabilities for me. So I'd like you to work out the probability that I win either 0 or 1 games. Do you remember that you do, this is a cumulative thing on the calculator, isn't it? What about the probability I win 0, 1 or 2 of them? And what about the probability that I win 0, 1, 2 or 3 of them? Can I get you to use your calculator to work out those 3 probabilities for me? So for those that are a little rusty, statistics mode, dist, binomial, BCD. So you set your lower and your higher. So if you want the probability of 0 and 1, you put 0 as your lower, 1 as your higher. Did you miss this as well, Kit? Sorry. Yeah, I apologise, Kit. Right. That sounds like Max is doing a great job. I've got some videos that can get you up to speed though, so I will. Yes, are we all calculating?
What's that? That's probably going to do it again. Yeah. And then sometimes you might get it. You might get it split this. Or the lower ones in there. It's 20. No, it's 20.
He wins 11 games. 0.9.
So I get, do you remember we round to 4 decimal places? It's just an unusual historical thing. Now, remember, this isn't the probability of 3. It's the probability of all of the possibilities up to and including 3. 0, 1, 2, and 3. And that's not super unlikely. That's not super unlikely. Okay, it's unlikely. We're expecting to get 5, but anything 3 or less, it's not super unlikely. So, you know, unlikely things do happen. Make no mistake, unlikely things do happen. But this, that's really getting unlikely, and this is, you know, stupendously unlikely. You know, this is, you know, less than 2% of the, just slightly more than 2% of the time this would happen, and just under 10% of the time this would happen. So what do we do? What do we do? Does that mean that if I only win 1 of the 20 games that we say, right, no, the probabilities must be wrong? Or if I win 2 of the games, does that mean the probability must be wrong? Well, here's what we say. We say, right, I am only going to suspect something is wrong if there's a particular level of unlikeliness. And we tend to describe that using a percentage. So we sometimes say we're going to test at the 5% level. The 5% level says, I'm going to suspect something is up, something is wrong, if the probability of what happens and the probability of up to that value is less than 0.05. At the 5% level, I think something's up if that is less than 0.05, 5% is a decimal. So if I was testing at the 5% level and won 2 of the games, that's not unlikely enough. But that would be unlikely enough. So if that had happened and I was testing at the 5% level, then I'm saying, no, that's too unlikely. 5% level means you're dealing with things that would only happen 5 out of 100 times. Sometimes we're a bit more broad. We test at the 10% level, which is where we say, right, I'm only going to think something is fishy if it falls in this region here that has a probability that's less than 0.10. That's not a particularly strong test because, you know, 10%, 10 out of 100 times, unlikely things do happen. So if I was testing at the 10% level, I would say something's fishy. Okay, so at the 10% level, this is suspicious. If that was the threshold of uncertainty I was dealing with, I'm only going to be interested in things that would only happen 10% of the time. If I was testing at the 5% level, that's fine, because that's more than 5%. But at the 5% level, that is very suspicious. What level do we use? Well, you're told that in the question. in the real world, that's a decision that people have to make. And that's sometimes referred to as the significance level. And we're just saying, you know, this is unlikely, but how significant is that unlikeliness? So at the 5% level, we're looking for a probability here that is less than a half. Not of the particular value that we got, but of 0 up to that particular value. And at the 10% level, we're asking, is that probability there, is that less than 0.1? From 0 up to that particular value. And these problems are actually set out in a particular way. So let's look at a sort of book example, and let's set it out in the correct way, okay? So here we've got an election candidate that believes she has the support of 40% of the residents in a particular town. So what that means is, if you go up to someone at random and ask them, do you support this candidate? There's a 40% chance they'll say, yes, they do. All right? That's my success-fail criteria. And this research is going to ask 20 people. Okay? So what we have here is another situation that can be modelled as binomial. In this case, we're dealing with that. Okay? X is our test statistic. X, in this case, is the number of people who say they will vote for our particular candidate. So when it says write down a suitable test statistic, I would write two things. I would write that, and then I would say where X is the number of people who would vote for the candidate. We then state our hypotheses. Okay, so this is the sort of the formal side of things. So at the moment, we believe that the candidate is correct. We call that our null hypothesis. So this candidate, our null hypothesis, H0, this candidate is stating that the probability someone votes for them is 0.4. So that's our null hypothesis, that's referred to as. That's the status quo. That's what we think is true at the moment. The null hypothesis. But we, for some reason, and sorry, that's we normally put H0 with a colon. Sorry, that's not coming out very clearly. But for some reason, we wonder if something's amiss, and we're not told why there's that suspicion. But for some reason, we wonder if the candidate's over-egging her popularity. So we have the alternative hypothesis, which we call H1, and that is that actually she's not quite as popular as she thinks. In this case, the probability is less than 0.4. We call that the alternative hypothesis. Alternative hypothesis. And at that point, I'd always draw a little picture. Because it could be that this researcher will ask 20 people and none of them will vote for the candidate, or they all might vote for the candidate, but I'm expecting 8 of them to vote for the candidate. 20 times 0.4. So 20 is what I'm expecting to happen. So that's my peak. Remember, these distributions are not symmetrical unless probability is a half. So 8 is where the peak will lie. But we want to test at the 5% significance level. So we want to know, does the probability of 0 to 3, which is what we actually got, is that less than 0.05? So, can I invite you to work out whether or not, in this case, we would reject this and suspect this, or whether we reject this and suspect this. Have a look at what she actually got was 3 people, much less than the 8 we were expecting, but is it just unlikely, or is it so unlikely as to be suspicious? Go on, see if you can change, still use your calculator, change your parameters and work out that particular one. Right, yeah, our lesson's going on. You should be in here just talking. You should be using the controller and then making a way up. Okay? Well, it doesn't need any gas. Can you make a way up? So we're testing at the 5% level. We're not working out the probability of 3, we're working out the probability of 0 to 3. So that's the thing that so it's really small, it's really unlikely, and in particular, in the context of this problem, it's less than 0.05. So this is much smaller than the threshold at which we're going to say our suspicions become founded. Now this doesn't absolutely mean that her support has fallen, because unlikely things still happen. So all we can say is there is evidence to reject the null hypothesis. So there is evidence to reject the null hypothesis. And I always say, and suggest that a popularity has fallen below 40%. And that sort of form of words is, pretty standard in terms of answering these questions. So we definitely reject the null hypothesis in this case, because that probability of 0 to 3 is much smaller than our 5% threshold. Yes, Arthur?
Why would we include the values lower than 3 in that?
So it's a really, really good question. It's the 5% threshold doesn't mean we're looking for. It doesn't mean that 3 would only. We think it's suspicious because 3 would only happen 5 out of 100 times. What we're saying is it part of the most unlikely 5% of results? Okay, so that's what the 5%. So it's a bit unlikely me saying that's only going to happen 5 out of 100 times, because actually it's far less than that, isn't it? Because it's part of the range of values that would only happen 5 out of 100 times. So it's always the range rather than the individual value. But yes, it is hard to perhaps get your head around. Oh. Okay. So I often use the phrase formulaic, don't I, with problems. These are quite formulaic problems in that they pretty much always look the same. So I want those 2 questions there. Right, so we're on page 101, and this is question 5 and 6, but I'm going to leave them on the board. So here we've got a situation where they suspect there's been a reduction in the proportion of faulty articles. Okay, and here we've got another candidate whose support has reduced. So see if you can, and I want us to not do what this has said, I want us to do what we just did. So take the value, so we've got 8 out of 100 in that case, and we've got 7 out of 20 in that case. I want you to actually say whether or not we can reject or accept the null hypothesis. So that's question 5 and question 6. Have a go at those 2. And try and get into the habit of setting out the problem in the way I did, with the test statistic, the null hypothesis, the alternative hypothesis, and a little sketch, okay? Okay, so hopefully with the first one, your test statistic was the number of faulty articles, which we're expecting to be 10. We actually got 8. The probability of 0 to 8, still pretty high. So it's certainly a lot bigger than 5%, so there is, and this is slightly relating to the previous one, isn't it? There is not enough evidence to reject the null hypothesis. Okay, so in the previous case we had enough evidence. In this case there is not enough evidence. Once you've finished number 6, I'm going to put an additional question on here which is slightly different. So with 6, again we were suspicious that someone was over-egging the level of their support. And for some reason we're using a much stricter level of significance here. So we're only going to reject the null hypothesis if the probability of 0 to 7 is less than 0.02. It's not, it's way bigger. In fact, at the 5% level it would still have been okay. We would have rejected it at the 10% significance level, but not at the 5 and certainly not at the 2. So there is, my dreadful handwriting, I apologise. These words, the former words are important. There is not enough evidence to reject the null hypothesis. So, as far as we are aware, we haven't got significant evidence to suggest that that has changed. And that's not the number of faulty articles, is it? That is the number of supporters, the number of people who would vote. I haven't changed it a bit. It doesn't mean that it's not wrong. It doesn't mean it's not wrong, we just haven't got the evidence. This is one test of 20 people. We can't base our entire decisions on that. Now, what was the subtle difference here? So Harrison, what was the subtle difference here? In what way was this one different from all of the other ones that we've done? It's in the statement of the alternative hypothesis. We suspect the probability is greater in this case. So what we're looking for here is an unusually big result. So in this case, we we're not told the context here, but it's something that could be 0 or it could be 30, and we're expecting it to be 6. And we actually observe 10. So when we are looking for probability being bigger than we think it is, we need to look at this end. Is that probability in the most unlikely 5% of probabilities? So when we do this, we need to test between 10 and 30, which used to be a real pain when we were working from the tables, but now our calculator tells us that. It's easy peasy. So we are testing at the top end. You know, is 10 unusually too big? So we're now not interested in something that's unusually small. We want to know if it's unusually too big. So we're looking at our top end, our right tail, rather than our left tail. I haven't done this one, so I'm awash with excitement. Is it going to be? So we're going from 10 to 30. Not far off, but it isn't significant enough. So 0.0611 is, it's bigger than a 5%. So there is not enough evidence to reject the null hypothesis.